welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 363, max sum of rectangle no larger than k. This problem challenges us to find the maximum sum of any subrectangle within a matrix, with the constraint that the sum must not exceed a given value k. Stay tuned as we explore the approaches and strategies to solve this challenging yet rewarding problem. In this problem, we are tasked with finding the maximum sum of a rectangle within a given Mxn matrix, with the constraint that this sum must not exceed a given integer k. A rectangle in the matrix is defined by a subarray of rows and columns, and our goal is to determine the largest possible sum of such a rectangle that stays within the limit of k. The matrix, represented as a 2D array, contains integers where each element at position I, j, corresponds to the value at the ith row and jth column. For the output, we are required to return a single integer, the maximum valid rectangle sum that satisfies this condition. It's important to note that the problem guarantees there will always be at least one rectangle in the matrix with a sum no larger than k. For example, consider a matrix 1, 0, 1, 0, minus 2, 3, and k equals 2. Here, the goal is to identify rectangles within the matrix where the sum of elements is no larger than 2. There are several possible rectangles, including individual elements like 1 and 0, as well as combinations of elements such as the sum of the subarray spanning matrix 0, 0 to matrix 0, 1, which equals 1. After examining all possible rectangles, the one with the maximum sum that does not exceed 2 is a rectangle with a sum of exactly 2. Thus, the output for this example is 2. Now let's look at another example. Suppose the matrix is 2, 2, minus 1, and k equals 3. Here, the matrix has only one row, but we can still identify multiple subarrays or rectangles. For instance, individual elements like 2 and -1 are valid rectangles. We can also consider rectangles spanning multiple columns, such as the sum of matrix 0, 0 to matrix 0, 2, which equals 3. However, some rectangles, like matrix 0, 0 to matrix 0, 1, result in a sum of 4, which exceeds k and is therefore invalid. The maximum sum among all valid rectangles is 3, so the output is 3. Now take the matrix minus 5, with k equals minus 2. In this case, the matrix contains only one element, which is minus 5. Since this value is already less than k, it is the only possible rectangle. Thus, the maximum valid sum of any rectangle in this case is minus 5. This example highlights how the problem can handle very small matrices and negative values for both k and the matrix elements. Finally, it's important to consider edge cases. For instance, a matrix with dimensions at the upper limit, such as 100x100, or a scenario where k is very large, like 10⁵, allowing all rectangles to be valid. Other edge cases include matrices with all negative elements and a negative k, or matrices with all positive elements where k is smaller than the smallest element in the matrix. Addressing these scenarios ensures the solution is robust and handles all possible inputs within the given constraints effectively. To solve LeetCode problem number 363, the task is to identify the maximum sum of any subrectangle within a matrix, ensuring that this sum does not exceed the given value of k. The challenge lies in balancing accuracy and computational efficiency, particularly when dealing with large matrices. One approach to consider is the brute force method. Here, we systematically iterate through all possible subrectangles by defining their top left and bottom right corners through nested loops. For each rectangle, we calculate the sum and keep track of the maximum sum that meets the condition of being less than or equal to k. While this approach is straightforward and easy to understand, it is computationally expensive. The time complexity is m²*n², since we need to explore all combinations of row and column pairs, making it infeasible for larger matrices. On the upside, it requires no extra memory, with a space complexity of 1. However, the inefficiency of this method makes it unsuitable for real-world scenarios where performance is critical. A more refined and practical solution is the optimized approach that combines row summation with a sorted data structure. In this method, we transform the problem into finding the maximum subarray sum no greater than k for every pair of rows. To achieve this, the matrix is compressed into a one-dimensional array by summing up columns between two rows. This reduces the problem from 2D to 1D for each row pair. Then, a sorted data structure like treeset in Java or sorted list in Python is used to maintain prefix sums. This structure allows efficient queries for the largest prefix sum that fits within the constraints. By iterating over all possible row pairs, we compute the column sums, update the prefix sums, and use the sorted structure to perform binary search operations. This optimization drastically reduces the time complexity to O m squared asterisk n asterisk log n, where the log n factor comes from maintaining and querying the sorted prefix sums. Space complexity is reduced to O n, making it scalable for larger inputs. While this approach is slightly more complex to implement compared to brute force, it offers a significant improvement in efficiency, making it a strong candidate for solving the problem effectively. Another alternative is to use dynamic programming in combination with Cadon's algorithm. Cadon's algorithm is typically used to find the maximum subarray sum, and here it can be applied across row pairs to compute the maximum subarray sum that satisfies the constraint of being no larger than k. However, this approach requires additional logic to prune sums that exceed k, which can complicate the implementation. In terms of performance, it has a time complexity of O m squared asterisk n, similar to the optimized approach, and a space complexity of O n. Despite its theoretical efficiency, the need for additional pruning logic makes it less intuitive and harder to implement than the row summation method. Ultimately, the chosen strategy is the optimized approach using row summation and a sorted data structure. This method strikes the best balance between efficiency, scalability, and clarity of implementation. By reducing the problem to 1D and leveraging a binary search-friendly structure, it avoids unnecessary computations and handles large inputs effectively. The trade-off in terms of slightly increased complexity is well justified by the substantial performance gains, making it the most practical choice for this problem. To solve the problem of finding the maximum sum of a rectangle in a 2D matrix that does not exceed a given value k, we start by breaking the problem into manageable steps. The first step involves pre-computing column prefix sums. By doing this, we can quickly retrieve the sum of any segment within a column. The idea is simple: for each column, calculate cumulative sums row by row, so that each entry in the prefix sum array represents the sum of all elements from the top of the column down to a specific row. For example, given a matrix like 1, 2, 3, 4, the first column's prefix sums would be 1, 4, meaning the sum of the first row is 1, and the sum of the first and second rows combined is 4. This pre-processing step is essential because it allows us to compute sums of subrectangles more efficiently in the subsequent steps. The next step is to iterate over all possible row ranges in the matrix. This is necessary because each row range defines a potential set of subrectangles to consider. For each pair of rows, say R1 and R2, we calculate the sum of all elements in the subrectangle bounded by these rows and all columns. Using the prefix sums computed earlier, we can determine the sum of any column segment within this row range in constant time by subtracting the prefix sum of the row above R1 from the prefix sum at R2. Once we have the sums for all columns within this row range, the problem reduces to identifying the maximum sum of a contiguous subarray across the columns that does not exceed k. This transformation effectively reduces our problem from working with a 2D rectangle to solving a 1D maximum subarray problem, significantly simplifying the computation. To efficiently solve the 1D maximum subarray problem for a given row range, we use a sorted set. This data structure allows us to quickly find subarray sums that meet the condition of being less than or equal to k. As we iterate through the flattened 1D array of column sums, we maintain a running cumulative sum. At each step, we insert the current cumulative sum into the sorted set. Then, through binary search, we look for the smallest prefix sum in the set such that the difference between the current cumulative sum and this prefix sum is less than or equal to k. This difference represents the sum of a subarray that satisfies our condition. By leveraging the sorted set's binary search capability, we can efficiently find the required prefix sum and update our result accordingly. This approach ensures that we maintain optimal performance while checking all possible subarray sums within the given constraints. The key to improving the efficiency of this algorithm lies in reducing its complexity. Instead of explicitly checking all possible subrectangles, which would require O n to the power of 4 time for an nxn matrix, we lower the complexity to approximately O n cubed asterisk log n. This is achieved by iterating over row ranges, reducing the problem to 1D using prefix sums, and leveraging the sorted set for efficient subarray sum calculations. The sorted set is particularly crucial because its ability to quickly insert and search cumulative sums allows us to find valid subarray sums in logarithmic time. Meanwhile, the prefix sums enable constant time computation of column segments, which is essential for reducing the 2D rectangle problem to a simpler 1D problem. These optimizations work together to make the algorithm feasible even for larger matrices. The algorithm relies on three key data structures to achieve its efficiency. First, the 2D prefix sum array stores cumulative sums for each column, allowing us to compute the sum of any vertical segment of the matrix in constant time. Second, the sorted set, which functions as a binary search tree, enables efficient insertion and retrieval of cumulative sums. Its sorted nature is critical for performing binary searches to find subarray sums that meet the condition of being no larger than k. Finally, the flattened 1D array temporarily holds cumulative sums for a specific row range, effectively reducing the 2D subrectangle problem into a simpler 1D subarray problem. These data structures work in tandem to ensure the algorithm handles the problem efficiently and within the desired time complexity. When implementing this algorithm, it's important to consider several edge cases. For example, in a matrix with all negative numbers, the algorithm should correctly identify the least negative number that does not exceed k as the maximum sum. Similarly, for small matrices, such as a single row or column, the algorithm needs to handle these trivial cases without unnecessary computations. Another critical scenario is when k is very large, in which case the maximum sum might simply be the sum of the entire matrix. The algorithm should avoid extra calculations in such cases. Regarding complexity, the time complexity is O, n cubed asterisk log n, where n represents the larger matrix dimension, and the space complexity is O, n, accounting for the 1D flattened array in the sorted set. These considerations ensure the algorithm is robust and performs well across diverse inputs. To solve the problem of finding the maximum sum of a rectangle in a matrix that does not exceed a given value k, we start by importing the necessary functions from the bisect module. The bisect_left function will help us locate positions in a sorted list, and insort will allow us to insert elements while maintaining the list's order. Inside the solution class, we define the maxSum submatrix method. First, we determine the number of rows and columns in the matrix and initialize max_sum to -infinity, as we are looking for the maximum possible value. We then set up a loop to iterate through all possible left boundaries of the column range. For each left boundary, we initialize an array called row_sums to store cumulative sums for each row. This array will be reset for each new left boundary. Next, we iterate through the right boundaries of the column range, starting from the current left boundary. For each column in this range, we update the row sums by adding the values from the matrix. This gives us the cumulative sum of the rows for the current column range. Now, to find the maximum subarray sum within this range that does not exceed k, we use a sorted list called prefix_sums. We initialize it with a 0, which represents the sum of an empty subarray starting at the top. We also maintain a running total, current_sum, which accumulates the row sums as we iterate through each row. For each row, we calculate the target value as current_sum k. Using bisect_left, we find the smallest prefix sum in prefix_sums that is greater than or equal to the target. If such a prefix exists, we calculate the potential maximum sum by subtracting this prefix from the current sum and update max_sum accordingly. After checking for a valid prefix sum, we use the insort function to insert the current prefix sum into the sorted list. This ensures that our prefix_sums list remains sorted, which is critical for efficiently finding the smallest prefix sum in subsequent iterations. By maintaining this sorted list, we can quickly compare and adjust as we process each row's cumulative sum. Once all rows and column boundaries have been processed, the loop concludes, and we return max_sum, which now holds the maximum sum of any subrectangle within the matrix that does not exceed the given value k. This approach effectively combines dynamic programming with binary search to optimize the solution for this challenging problem. Here, we begin by defining our solution class and implementing the maxSum submatrix method, which takes a 2D matrix and an integer k as input. The goal is to find the maximum sum of any rectangle within the matrix that does not exceed k. First, we initialize the dimensions of the matrix, the number of rows and columns, and set a variable maxsum to the smallest possible integer value to keep track of the maximum sum found so far. The outer loop iterates over all possible starting columns, represented by left. For each starting column, we create an array called rowsums to store cumulative sums of each row for the current column range. Next, we use another loop to iterate over all possible ending columns, represented by right. For each column pair, left, right, we update the rowsums array by adding the values of the matrix for the current column right to the respective rows. This effectively calculates the sum of each row in the rectangle defined by the column range, left, right. To find the maximum subarray sum within the current column range that does not exceed k, we use a tree set to maintain prefix sums. A tree set is useful here because it allows efficient lookup and insertion while keeping the elements sorted. We start by adding the value 0 to the tree set to handle cases where the subarray starts at the beginning of the row. We then iterate through the rowsums array, calculating the cumulative sum current sum as we go. For each cumulative sum, we use the tree set to check if there exists a prefix sum such that the difference between the current sum and this prefix is less than or equal to k. This is done using the ceiling method, which finds the smallest prefix sum in the tree set that is greater than or equal to current sum k. If such a prefix is found, we calculate the sum of the subarray as current sum target and update max sum with the maximum value between its current value and this new subarray sum. After checking for the prefix, we add the current sum to the tree set to keep track of all prefix sums encountered so far. This process ensures that we evaluate all possible row sums within the current column range while maintaining the constraint that the maximum sum does not exceed k. Once all possible column pairs and their corresponding row sums have been processed, we return max sum as the result. This approach efficiently combines prefix sums and binary search via the tree set to handle the constraints of the problem, ensuring that we find the optimal solution within the given matrix. To begin solving this problem, we initialize the matrix dimensions as rows equals 2 and cols equals 3, and we set max_sum to -infinity. The goal is to find the maximum sum of any rectangle in the matrix that does not exceed k equals 2. We start by iterating over the left boundary of the rectangle, setting left equals 0, and initializing row_sums to 0, 0, to represent the cumulative sums of rows between the left and right boundaries. Moving to the inner loop, for right equals 0, we include column 0 in the rectangle, updating row_sums to 1, 0. Now, we use a sorted list prefix_sums initialized to 0 to efficiently track prefix sums of cumulative row values. For row 0, we calculate current_sum equals 1 and determine target equals current_sum k equals -1. Using binary search with bisect_left, we find that there is no valid prefix sum smaller than or equal to target. Therefore, we insert current_sum into prefix_sums, updating it to 0, 1. For row 1, the current_sum remains 1, and the target is again -1. Similarly, no valid prefix sum is found, so we insert 1 into prefix_sums, resulting in 0, 1, 1. At this stage, we have not found a rectangle with a sum greater than -infinity that satisfies the constraint. The maximum subarray sum less than or equal to k remains 1. Next, we expand the rectangle by including column 1, setting right equals 1 and updating row_sums to 1, -2. After resetting prefix_sums to 0, we process row 0, or current_sum equals 1 and target equals -1. Again, no valid prefix sum is found, so we insert 1 into prefix_sums, resulting in 0, 1. For row 1, current_sum becomes -1, and target equals -3. No valid prefix sum exists, so we insert -1 into prefix_sums, updating it to -1, 0, 1. Next, including column 2 by setting right equals 2, we update row_sums to 2, 1, and reset prefix_sums to 0. For row 0, current_sum equals 2 and target equals 0. A valid prefix sum is found at index 0, so we update max_sum to the maximum of its current value and the rectangle sum, which is 2, 0 equals 2. We then insert 2 into prefix_sums, making it 0, 2. For row 1, current_sum equals 3 and target equals 1. A valid prefix sum is found at index 1, but the max underscore sum remains 2 since 2 equals 1 is smaller than the current max underscore sum. Thus, the final output for this example is 2. Now, we move to a larger matrix where rows equals 3 and cols equals 3, and the goal remains to find the maximum rectangle sum no greater than k equals 8. We start by initializing max underscore sum to negative infinity. Setting left equals 0, we initialize row underscore sums to 0, 0, 0, and begin processing rectangles. For right equals 0, we update row underscore sums to 2, 3, minus 1, and initialize prefix underscore sums to 0. For row 0, current underscore sum equals 2 and target equals -6. No valid prefix sum is found, so we insert 2 into prefix underscore sums, updating it to 0, 2. For row 1, current underscore sum equals 5 and target equals -3. Again, no valid prefix sum exists, so we insert 5, resulting in 0, 2, 5. For row 2, current underscore sum equals 4 and target equals -4. No valid prefix sum is found, so 4 is inserted, making prefix underscore sums equals 0, 2, 4, 5. At this point, the maximum subarray sum is 5. Expanding the rectangle to include column 1, row underscore sums becomes 4, minus 1, 0, and prefix underscore sums is reset to 0. For row 0, current underscore sum equals 4 and target equals -4. No valid prefix sum is found, so we insert 4, resulting in 0, 4. For row 1, current underscore sum equals 3 and target equals -5. No valid prefix sum exists, so we insert 3, updating prefix underscore sums to 0, 3, 4. For row 2, current underscore sum equals 3 again, and no valid prefix sum is found. We insert 3, making prefix underscore sums equals 0, 3, 3, 4. Finally, we include column 2, updating row underscore sums to 3, 1, 4, and resetting prefix underscore sums to 0. For row 0, current underscore sum equals 3 and target equals -5. No valid prefix sum is found, so we insert 3, resulting in 0, 3. For row 1, current underscore sum equals 4 and target equals -4. No valid prefix sum exists, so we insert 4, making prefix underscore sums equals 0, 3, 4. For row 2, current underscore sum equals 8 and target equals 0. A valid prefix sum is found at index 0, so we update max underscore sum to 8, which is the maximum of its current value, and 8, 0 equals 8. Thus, the final output for this example is 8. In this edge case, we have a single cell matrix with rows equals 1 and cols equals 1, and the goal is to find a rectangle sum no greater than k equals 3. We initialize max underscore sum to negative infinity and set left equals 0, initializing row underscore sums to 0. For right equals 0, we update row underscore sums to 5 and initialize prefix underscore sums to 0. For the only row, current underscore sum equals 5 and target equals 2. No valid prefix sum is found, so we insert 5 into prefix underscore sums, making it 0, 5. Since no valid rectangles meet the condition, the maximum subarray sum remains negative infinity. The final output for this edge case is INF. The time complexity of this solution can be broken down step by step. First, consider the outer loops over the columns. We start with the left column, iterating from 0 to cols 1, and for each left, we iterate over right, which ranges from left to cols 1. Together, these loops allow us to evaluate all possible column pairs in the matrix. The number of iterations here is the sum of the first cols natural numbers, which simplifies to cols asterisk, cols plus 1/2. This gives us a contribution of O, cols caret 2, to the overall time complexity. Next, within the right loop, we calculate the cumulative row sums for all rows during each iteration. Since this involves processing rows for each column pair, the operation requires O, rows, time. Combining this with the O, cols caret 2, column pairs, the total cost so far becomes O, cols caret 2 asterisk rows. This sets the stage for the next computational step. Now, let's analyze the prefix sum and binary search operations. For each row sum array, we use a sorted list called prefix underscore sums to store cumulative sums. Two key operations occur here: bisect underscore left, which performs a binary search to find the smallest prefix, and insort, which inserts the current prefix sum while maintaining the sorted order. Both of these operations have a time complexity of O log rows, since the size of prefix underscore sums is proportional to the number of rows. These operations are performed for each row in the matrix, so the total cost per column pair is O rows asterisk log rows. When we consider all column pairs, this results in a total contribution of O cols caret 2 asterisk rows asterisk log rows to the overall complexity. Combining all the steps discussed, the dominant term in the time complexity is the prefix sum in binary search operations, giving us a final time complexity of O cols caret 2 asterisk rows asterisk log rows. The space complexity of the algorithm is relatively straightforward. First, we use an array called row underscore sums to store the cumulative sums for all rows. This requires O rows space. Additionally, we maintain a prefix underscore sums list to store running prefix sums for each row sum array. The size of this list is also proportional to the number of rows, so it contributes another O rows to the space complexity. Beyond these, the algorithm uses a few additional variables such as max underscore sum, current underscore sum, and loop counters, but these require negligible space, or O1. Therefore, the total space complexity of the algorithm is determined by the row underscore sums and prefix underscore sums arrays, resulting in an overall space complexity of O rows. Let's discuss the best, average, and worst case scenarios for the algorithm. In the best case, the time complexity remains the same because the algorithm must iterate over all column pairs and rows regardless of input. However, if k is very large, the bisect underscore left operations can become trivial since no prefix subtraction satisfies current underscore sum prefix k. This might slightly reduce constant factors in practice. For the average case, the algorithm performs as described, with no significant deviations from the calculated time complexity. In the worst case, when k is small, the binary search operations are maximized for every row sum, but the overall time complexity remains O cols caret 2 asterisk rows asterisk log rows. Comparing this to a brute force approach, which calculates the sum of every possible submatrix, the difference is significant. A naive method would require O rows caret 3 asterisk cols caret 3 operations, which is impractical for large matrices. By leveraging prefix sums in binary search, this optimized algorithm reduces the complexity to O cols caret 2 asterisk rows asterisk log rows, making it far more efficient. Finally, let's mathematically validate the derived time complexity. The outer loops over column pairs contribute O cols caret 2 as we evaluate all possible pairs of columns. For each column pair, calculating the row sums adds an O rows factor. Additionally, the prefix sum operations, which involve binary search and insertion, contribute O log rows per row. Multiplying these together, the total time complexity becomes O cols caret 2 asterisk rows asterisk log rows. This result is obtained by systematically analyzing the contribution of each step and summing the terms. The final complexity confirms the efficiency of the algorithm, especially when compared to the brute force approach. When tackling this problem, one common mistake is using a naive O n to the power of 4 approach that iterates over all possible submatrices. While this might work for smaller inputs, it quickly becomes impractical for larger matrices due to time constraints. Instead, it's important to use optimized algorithms, such as the prefix sum combined with a sorted set approach, which operates in O n squared asterisk m asterisk log m time. Another mistake to avoid is overlooking edge cases. For example, single row or single column matrices can behave differently compared to larger grids. Similarly, when k is negative or very small compared to the matrix elements, or when all elements in the matrix are negative, these situations require careful handling to ensure the solution remains correct. Lastly, prefix sums are a powerful tool here, but they can lead to errors if not reset properly for each new row range. Always ensure that calculations are independent for every row pair to avoid carrying over incorrect cumulative sums. Another pitfall is misunderstanding how to use binary search with sorted sets, such as a tree set or sorted list. The key is to find the smallest prefix sum that satisfies the condition current underscore sum prefix underscore sum equals k. Many miss this critical step, leading to incorrect results. Additionally, in languages like Java, you must be cautious about integer overflow when handling large values of k or matrix elements. Use data types like long to safely store large sums. From an interview perspective, it's essential to demonstrate your ability to reduce a 2D problem into a manageable 1D problem using techniques like prefix sums. This dimensional reduction is a skill interviewers often focus on, so be sure to explain the transition clearly. Similarly, proficiency with the sorted set and binary search technique is vital. If this is an area of weakness, practicing related problems can help solidify your understanding. Finally, it's good to discuss trade-offs in your solution. For example, explaining why a brute force O, n to the power of 4, approach is infeasible and emphasizing the efficiency of the optimized O, n squared asterisk m asterisk log m solution shows strong analytical skills. When solving this problem in an interview setting, explicitly addressing edge cases can make a strong impression. For instance, consider what happens when k is negative or when the matrix contains only negative numbers. Mentioning these scenarios demonstrates that you approach problems thoroughly and systematically. Another useful insight is recognizing that this problem is an extension of the classic maximum subarray problem, which is solved using Cadon's algorithm. By relating this 2D variation to the simpler 1D problem, you can explain your thought process more effectively. Additionally, practicing related problems can deepen your understanding. For example, LeetCode 560 focuses on finding subarray sums in 1D arrays using prefix sums and hash maps. It's a simpler version of this problem and a great way to build foundational skills. Of course, the current problem, LeetCode 363, should be practiced with variations in constraints and edge cases. Another related challenge is LeetCode 85, which explores finding the largest rectangle in a binary matrix. It shares similar techniques around dimensional reduction, making it an excellent complementary problem to study. Another relevant problem is LeetCode 209, which deals with finding the minimum size subarray sum. While this is a 1D problem, it requires efficient techniques like sliding windows or prefix sums, making it great practice for handling constraints. Now, turning to alternative approaches, the brute force method involves enumerating all possible submatrices by fixing their top left and bottom right corners. While this is simple to implement, its O, n to the power of 4, complexity makes it impractical for larger inputs. The optimized prefix sum combined with a sorted set approach is the most efficient general-purpose solution. By reducing the problem to 1D for fixed row ranges and dynamically managing prefix sums with a sorted set, it achieves a complexity of O, n squared asterisk m asterisk log em. Finally, dynamic programming can sometimes be used in special cases, such as when k is very large. This approach pre-computes sums to save computation time but may require more memory. Each of these methods has its strengths and trade-offs, so understanding when to apply each is crucial. That wraps up our discussion of LeetCode problem number 363, max sum of rectangle no larger than k. We've covered the problem requirements, walked through efficient approaches, and highlighted key takeaways. Thank you for joining me today, and don't forget to practice similar problems to sharpen your skills. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!